Okay, before I start, I want to say a few things, okay? You have been very good. You were listening onto the overview, especially when there are not too many blanks. Just listen, make some notes, all right? Second, my convention is like this. You see black color means it's printed, no need to copy. Blue color means there are blanks, you just copy. Red means important. You decide whether you want to copy or don't want to copy. Follow? Can. Okay, not going to talk about all this. See, sometimes I will skip parts of the notes because they are inside, you can read on your own. All right? Essentially, what we are going to talk about is, like I say, right, you pick three, consider data point. 3, what is the distribution of the sample mean? Look, when I look here, when I say I pick 160, 162, 164, and then I divide by 3, I get 162. Do you all think that this 162 is the population mean? Is it the population mean? Population mean means if I sample all 1006 of you, divide by 1006, the height of all of 1006 divided by 1006, do you think it's equals to 162? No, right? This 162 is just randomly pick 3 and divide by 3. Correct? It's not the it is not the population mean. 162 is what we call the sample mean. Correct? Yes? So, each sample statistic, that means just now we talked about, the example I can quote is just now the 162, right? Correct? Each sample statistic, this 162 obtained, is just an estimate of the actual population parameter. Correct? The actual mean height of a student in VJC is not 162. Follow? Because I only pick 3. Okay. When we study stats, of course, there are only two things that we are there are two main things that we're interested in. One is the population mean, which most of the time we don't know. Now, if we know as population mean, there's nothing to sample, no need to sample already. Correct? And population variance. Okay, now, let's go through this exercise, okay? This is an exercise that all of us should be able to follow. Pretend that we have one fair six-sided die. Okay, one fair six-sided die, that means the die look like this. Two faces numbered 1, that means 1, 1. Another two numbered 2, that means 2, 2, and on. So we have 1, 1, 2, 2, 3, 3. Suppose X is the random variable representing the outcome of a toss, then the probability distribution of X is what? Can fill in? Can, right? Because there are only 3 possible outcomes. X can only be 1, 2, or 3. Right? What goes into here? This is the probability X equals to 1. Because there are 2 faces, correct? So therefore this must be 2 out of 6 or 1/3. Okay? This one, there are also 2 faces. They are numbered 2, just 2 out of 6 or 1/3, and 1/3, 1/3, 1/3. No problem. It's quite easy, everybody knows how to calculate. Right? What are we trying to do here? Now, given this probability and this probability distribution, I don't think you quite remember this formula. I don't think so, but let us try and make sense of this expected value of X. Expected value means, what is the mean? What's the mean? Actually, without calculation, we all should know. Intuitively, you know. If you do enough times, throw the die enough times, and then take average, long-term average, between 1, 2, and 3, obviously the long-term average is 2. Does it make sense? Because all equally likely, right? 1, 2, and 3 are all equally likely. Correct? And long-term average, you should get 2. This one, without any calculation, even you ask probably a Sec 2, Sec 3 student, intuitively you know the long-term average is 2. Does it make sense to all of us? Although, yes, right? But let's try and make sense of this formula. This formula says this. Now, first you take 1 times 1/3, 2 times 1/3, 3 times 1/3, and you sum them all up. That you will get the mean. Does it make sense to all of us? I think it does. That means the more likely the number is, the higher the weightage. Make sense? Make sense, huh? So intuitively it makes sense. Don't need to really understand the proof, but intuitively this formula makes sense. This times this, this times this, this times this. Now can you imagine if 1 is more likely? That means this probability is very big. Maybe 2/3. Then you think the mean will be smaller than 2. Do you all follow what I'm saying? Does it make sense? Is that right? So this one, I know you all cannot remember, or rather this doesn't sound familiar to you, but I'm trying to make sense of how this formula comes about. Follow. Next, variance. Variance, this one again very alien to all of us. This one, I just want to say a few things. You all can make notes. This one is from Stats 1. This is from Stats 1. But never mind, I'm sure you all cannot remember. Look, what does it say? It says that first what I do is take the x minus mu. That means it's the distance from x to the mean. Basically, variance measures spread. Correct? The larger the variance, the more well spread the data is, the distribution is. So what we are saying is take x minus mean, in this case the mean is 2, then square it, then times the probability, then this take this minus 2, square it times the probability, this minus this, square it times the probability. Maybe I show you the working and it makes a bit more sense to all of us. Individually, you take this minus 2, this minus the mean. This is the mean. 2 is the mean. What's this? 2 is the mean. 2 is the mean. 2 is the mean. Individually, you take them. Minus mean, minus mean, minus mean. Then square, then times the probability. Remember, variance measures spread. So what we are saying is we have to measure the spread of the data. I'm not going to prove it, okay? I'm not going to prove this formula. But intuitively, I hope it makes sense to all of us. Okay. Then we accept this formula and then we get these two numbers. Now, can I emphasize here? What we are saying is this. I have a distribution. I have a random variable x, which is the score on a die, and I've calculated that the mean is 2, the variance is 2/3. So far so good. And one throw, one toss only, the score on one toss. Now next, I'm going to consider a situation where I take 2 tosses. I toss it 2 times. And I observe the outcome. Now this exercise I'm going through is to simulate a case of, like just now I mentioned, right, I take 3 guys, take x1, x2, x3, divide by 3. Correct? I want to find out the distribution of x1 plus x2 divided by 2. Follow what I'm saying? Okay? Okay, now let's do this. If I take 2 tosses, 1 time, 2 time, there are many possibilities. I have listed 3 of them down. Correct? I have listed 3 of them down. It could be 1, 1. It could be 1, 2. The order doesn't matter. Order matters. Order matters. Order matters. So there are many, many possibilities. You can write down. No problem. Let's write down. Okay? You can be faster than me and you can write down. Okay? 2, 1. Order matters. That means the first toss, second toss. First toss. First toss, second toss. You know you can write, okay? I don't want to write, you're right. Then 3, 1. Lazy, Okay, for completeness, right. So fickle. Okay, again. So far so good. You have all these possibilities. No other possibility already. 9. Correct? Yes. What are we about to do? Focus on here. Sample mean. Sample mean. Sample mean means what? Means I take the 2 score, divide by 2 lah. Okay. 1 minute, quickly fill them all up. Next, what about the probability? Probability also makes sense because what is the probability you get a 1 followed by 1? You just 1/3 times 1/3. 1 followed by 2, 1/3 times 1/3. 1 followed by 3, 1/3 times 1/3. All of them should have the same probability 1/9. And you total them up, of course, should be 1. Total probability must be 1 for sure. Now we can then table the sampling distribution of X bar. Look, this is different from X now because your X bar can take on 0.5s. Follow what I'm saying? Just now you remember the earlier table, only 3 possibilities, 1, 2 or 3. But when you take X bar, take 1 and 2, divide by 2, you get 0.5s. Now, look. Are we able to fill this up? Yes? You can get 1, 1.5, 2, 2.5 or 3. What is more critical is this. See, now you have these 2 extra values. What's the probability that you get 1? 1/9. Because there is only one case. Look here. There is only this one. The rest, correct? So, to get 1, the probability is 1/9. What about 1.5? Be very careful, you don't assume that it's just 1/9. Because you could have this and this, both and having a probability of 1/9. So actually the probability is 2/9. Okay, I don't want to insult intelligence by saying more, okay? The rest you can fill up. Wow, what happened? Now, I want to emphasize, okay, the more important fact is this is the sampling distribution of X bar, and I want to say the X bar is just X1 plus X2 over 2. Right, because you take 1, toss 1 time, toss second time, take average. Follow? Okay, now, interesting, okay? Shall we make a quick guess? What do we think is the expected value of X bar? Don't calculate, okay? Don't calculate. If you know the formula, you can calculate, but intuitively, what do you think should be the expected value of X bar? Intuitively, 2? Yes? Intuitively, yes, 2. Without calculation, you know it's 2. And you're right. But never mind, let's prove to ourselves, because mathematics, we have to rely on formula just to prove to ourselves. Though most of the time, intuitively, we are right. Most of the time, I'm not saying all the time, okay? Most of the time, intuitively, we are right. You take this times this times this times this, then you realize that by calculating, you know it's 2. After calculating 2, we are able then to calculate the variance. Recall variance is the spread, okay, the distance from the X bar, this one, to the mean, which is 2, because this is obtained from here, correct? Tell me, just now our variance of X, just now our variance of X was 2/3. what do we think? Do we think the variance is still 2/3? Yes or no? Do we think it's still 2/3? Or can we make some guess what is the variance? Don't know. Am I? Talk to the friend next to you. Guess what is the variance? 30 seconds. Guess. Is it 2/3? Not 2/3? More than 2/3? Less than 2/3? Do you think it's more or less than 2/3 or equal to 2/3? There are only three choices lah. Right, it will be a number. More, less, or equal. More, less, or equal. Okay lah, you go and take it and calculate lah. But I think it helps us if you can make a guess, then we calculate. Calculate later, we'll calculate, no problem. Okay, I think 30 seconds is up. Okay, let's do this. Why don't we calculate and see what happens? Okay, why don't we just calculate and see what happens? Let's do this together. Calculate. How do we calculate? You take this 1 minus 2 times 1/9, a square times 1/9 plus 1.5 minus 2 square times 2/9 plus 2 minus 2 square, of course is 0, times 3/9 plus 2.5 minus 2 square times 2/9 plus 3 minus 2 square times, actually the numbers are quite nice. You realize that, of course this is 0. This and this are the same. This is just 1/4 times 2/9, which is times 4/9. Then you will get 1/9. Correct? Then these two numbers are the same. You get another 2/9. You get 6/9. Correctly? Wrong lah. 1/4 times half times 1/9. Correct? 1/9 plus another 2/9. Correct? This plus this is 1/9. Then this plus this, sorry. Correct lah. Anyway, you do some mental calculation, you know. Answer is 1/3. Correct? This plus this is 1/9. This plus this is 2/9. So you get 3/9. Now, compare. The first one, we have made an observation. The expected value of x and the expected value of x bar are the same. Very important. I think intuitively we know. I take 2 tosses divided by 2, 2 tosses divided by 2. The long-term average of it should be the same as taking 1 toss. Make sense? Now, interestingly, have attention please. The variance are not the same. How are the variance related? In this case only, okay? When I take average of 2, in this case, the variance of x bar is half of the variance of x. Because the variance of x was 2/3. The variance of x bar now is 1/3. Okay, now we only talk about 2 tosses. Later we talk about more. I just want to introduce a notation. Look, x was the result of tossing 1 time. When I write x1 and x2, they are independent observations of x. Okay, x1, x2 are independent observations of x. Independent means the first toss and the second toss don't talk to each other. The result won't affect each other. Correct? Yes? The result won't affect each other. Now, just now we were talking about the distribution of x bar is the distribution of x1 plus x2 divided by 2. Okay. At this point, some of your friends are sleeping. Can I suggest that you help them by waking them up? Okay? Yeah, next to you. Help them, okay? If they want to continue to sleep, then I will suggest to them that actually no need to come for lecture. Oh, really? I believe in that. No point coming to lecture theatre to sleep. You might as well go library and sleep more comfortable. Right, seriously. Okay, wait. Wow, I can't imagine I spend so much time on this. Okay. Goodness. Okay, yes, more on. Now, we are about to prove it. Prove the result. Prove what result? We are about to prove this result mathematically. We are about to prove, this result and this result. How? Can you have attention, please? I don't know whether you remember in stats 1, we had all these. I think you remember because we need to use them for CT2. Right? Okay. Now let's try and do this. Expected value of x1 plus x2 is equal to expected value of half x1 plus half x2. Now, the way we manipulate, can you have attention please? The way we manipulate this and treat this is as if you have expected value of x plus y over 2. Remember when x plus y? Yes, you have no problems. Now just treat as x plus y because x1 and x2 are two independent observations of x. Independent. Let me pick one, toss one time, toss second time. So, you shouldn't have any problems. It is half expected value of x1 plus half expected value of x2. Now, whether it is x1 or x2, expected value of x1 or x2 should be the same. Correct? You expect one toss, long-term average should be 2. The other toss should also be 2. So, therefore, it is just half times 2 expected value of x. Therefore, it is expected value of x. Now, notice throughout here, in the proof, I have not referred to the tossing experiment, or rather the numbers in the tossing experiment, which actually means that this is true for all x. Do you all follow what I'm saying? Could we do it for variance? Can. Let's do this. Be very careful, okay? Which is, remember the square? Sorry, there's a square. Just take note there's a square, yeah? Which is now, therefore, half square times 2 times variance x. Because variance of x1 and variance of x2 should just be variance of x. Therefore, you will get a half variance x. Now, again, I say throughout this proof, I have not referred to the Dr. Dye tossing experiment. Now we are only talking about sample of 2. Yeah, 2. Let's now, in general, let x be a random variable. And we have n independent observations of x. That means x1, x2, x3, x4 all the way to n. Not x1, x2 only, all the way to n. And each xi has the same probability distribution of x. Now, is it obvious to all of us now of course, whether it is this one is x1 or x2, x3, expected value xi is equal to expected value x. This is obvious, which we have made use many times. The variants are the same. Variance of x1, variance of x2, x3, x4 must be variance of x. This one no need you to copy. It can be easily shown. These two results, that first, let's take a look at number 2 first, okay? Don't worry about number 1 first. It can be easily shown that the expected value of x bar, which is finding x1, x2, x3, x4, all the way to n divided by n. This one, x bar is this, divided by n. Is the same, expected value of x bar is mu, and variance of x bar is variance of x divided by n. We have shown earlier when n is 2, then variance of x bar is variance of x divided by 2. Remember I have to say that in the die tossing. Does it make sense? We have shown the case when it's 2. Now all I'm trying to say is it can be shown that no matter what is n can be 3, 4, 5, 20, it is just variance of x divided by n. Follow so far? It can also be easily shown that if I have now look here, if I have t, which is x1 plus x2 plus x3 all the way to xn, this is what we call the sample sum. It can be easily shown that the expected value of the sample sum is n times mu, and the variance is n times variance. I don't think it's difficult to show lah. I don't think it's that difficult to show. This result we will make use of time and time and time again. Alright, Ken? Is that alright? Okay. A bit heavy. Pause a while.